I did 45 minutes of recording, then realized I forgot to hit the record button. Hello, all my JavaScript friends. This is TheVirtuoid, aka Mike Smith, and this is our racing game. Yes, it's a midweek extra video because I got the physics working on the car, with one tiny little exception that we'll be talking about a little bit later. So let me show you what I got here. Let me uncomment out the physics. Let me hit Control S, and there goes the car. We had a little bit of shimming in the wheels, but again, we'll get to that a little bit later. But there goes the car. Doesn't it look nice? And boing, it hits the wall. So let's go through how that actually works now. Why it was going flying all over the place in the previous videos, and what you could probably expect for the series end video this coming Tuesday. So let's go ahead and take a look first of all at our code. So this is the code that we're using. What I'm going to do here is I'm going to first of all turn off the physics for right now to kind of show you what's going on. And also going to go back up here, and I'm going to turn off the model. And what I've done here, I've got a couple of variables that I'm using to help me with this video to show you kind of what's going on with it. So by turning on by showing the chassis, and by turning off the model, by hiding the model, once we hit save, we'll end up with something like this on the screen. And everything we're going to do for right now is going to concentrate specifically, oh, good view. This is going to concentrate specifically on this particular screen. So as you can tell here, we've got basically 5 different meshes that we have our car. We have the chassis in the middle, that's that big white bar, and we have the 4 wheels. And yes, I do not have the wheel texture yet. I actually tried to do it, but it really looked horrible, so I'm going to just keep with this for right now. But the idea here is that let me show you how all of this part here works, and that once I get that, that's going to allow me to go into the discussion of about the 6 degrees of freedom constraint. All right, so first of all, the idea here is that we need to be able to position the wheels based upon the model itself. You know, because if you remember on the video there, the model that I showed you at the very beginning, the wheels were nicely aligned within the wheel wells. And to be able to do that, I've developed some data for each one of the different wheels, and there's some very important pieces of data here. First of all, the X and the Y. And this allows me to be able to say, you know, okay, based upon relative from the origin of the mesh, and within each mesh the origin is 0, 0, 0. So that's the coordinate system, x0, y0, z0. So relative from the chassis mesh itself, where is this wheel located? Like for instance, this is the right front wheel. If we go here, this right here is the right front wheel. Where is this located? The x-axis is the long piece right here. The z-axis is the crossbar, the axle basically. The y-axis is the up and down. The y-axis I'm not worried about whatsoever at this particular point in time. But this is the x-axis again is the lengthwise. The z-axis is the axle size, you know, the width. So if we go back to our code here, I'm basically saying the right front data, or the right front wheel, is going to be located 1.1. It's going to be 1.1x from the center of the chassis, and a negative 0.8 z. And what that will do is that will put that point exactly smack dab in the middle of this wheel. So each one of these particular pieces of data here, the x's and the y's, negatives and positives, will place that position data exactly in the middle of the wheel. And it's from there that we're going to figure out the position and grow the wheel, which is what we're going to get to next. Oh, and the x multiplier and the z multiplier, that basically says, you know, in relative to the position of the chassis, where is this wheel located? You know, for instance, the z multiplier for the right front wheel, we want to go positive on the x-axis to get to where the wheel is located, and we want to go negative on the z-axis, and that's going to become very important when we do the pivot points, as we'll show you here shortly on the 6 degrees of freedom constraint. So the important thing here is building the wheels. And before we build the wheels, there's a couple of pieces of information that's going to be extremely important for you to know, because this is where we're going to get into the big part of it. This is what I'm looking for, the 6 degrees of freedom constraint, physics 6 DOF constraint. What does this mean? This basically is the general catch-all physical constraint for Babylon JS that allows me to have complete control on how I want a particular mesh to interact with another mesh in the real world. And it's called 6 degrees of freedom because I have the x-axis, the y-axis, and the z-axis with both the positive and the negative on each side. So I've got basically 6 degrees of freedom. And based upon those 6 degrees of freedom, I'm able to tell it how it's going to interact. And there's a couple of very important pieces on here. This happens to be the wheel constraint, and we'll be getting to the collision box constraint later. And the collision box we'll explain when we get to it. But this happens to be the wheel constraint. So what I want you to imagine is that you have a wheel, and a wheel, you have an axle that goes into the wheel. There is a pivot point where the axle connects up to the wheel from the relative position of the axle. There's a pivot point that says, okay, I've got a point that is at the end of the axle that connects up to the wheel at the middle of the wheel. From the wheel's point of view, there's also a pivot point where the wheel says, okay, right smack dab in the middle of my construction here, I've got a little pivot point where I hook up to the axle. So with the 6 degrees of freedom, we have 2 different bodies we need to connect up, and each body is going to have a pivot point. And that's what's represented for pivot A and pivot B. Pivot points are vector 3 locations that are relative to the local coordinate system. Now, what do I mean by local coordinate system? Well, let's go back to the screen. The local coordinate system is the coordinate system based upon the mesh itself. For example, the local coordinate system of the chassis, the big white bar, has a 0, 0, 0 right smack dab in the middle. And of course, then it has a negative x and a positive x, a negative y and a negative z and a positive z, and a negative y and a positive y. Same thing with the wheels. It has a positive x, positive z, positive y, negative y. So that the local coordinate system is everything is based upon how the coordinate looks to the viewpoint of the mesh itself, with 0, 0, 0 being the absolute center of the mesh. The world coordinate system is everything else that's around here. So the world coordinate system will say, okay, although this right front tire happens to be at 0, 0, 0 from a local coordinate system, it may be at 10, 20, 30 or whatever within the world coordinate system. So every mesh, the world coordinate system tells you where the mesh is physically located in the world, while the local coordinate system says where are different things located based upon me, myself, and I. And so that's very, very important to understand. I didn't understand that in the last videos that I did, or the last constructions I did. That's why things were going so wrong. Pivot A, in this particular case, I have determined pivot A is going to be my chassis. Pivot B is going to be my individual wheel. So the idea here is I want to be able to find that pivot point in pivot A that is right up against the wheel, right up against the outside of the wheel. And I want pivot B to be from the perspective of the wheel at the exact same point. So pivot A and pivot B should be exactly the same from the world coordinate point of view, but they may be different themselves because pivot A is in relationship to the chassis mesh, while pivot B is in relationship to the wheel. Yeah, that's what it is. So let's take an example here. Let's go back to building our wheel. And very simply, I got a diameter of X, Y, and Z. I'm using a sphere. That seems to work a lot better. In my earlier videos, I had used capsules because those work nicely, but the spheres work even better now because now that I got everything right, the spheres work a whole lot better. And luckily, the sphere allows you to be able to give different diameters based upon the different axes. If all of them are exactly the same, you create a perfect sphere, but I don't want that. If you go back to the picture of the car here, the X and the Y axis are exactly the same, and that gives you the nice round number, but the Z axis is really, really thin, and that gives you the more car-like appearance. And so what I've done here is that I got diameter Z is basically a quarter of the diameter of the X or the Y or the wheel height itself. And then I just create all that, no biggie whoop here. Here's the important thing, the pivot point. So again, I got two different pivot points. I got a pivot point in relationship to the chassis and a pivot point in relationship to the wheel. First, let's build the pivot point in relationship to the chassis. Let's go over to our car. And our car, basically, the pivot point I want to do on the car here, and I want to use the right rear, or the back right wheel as an example, because it's right here. The pivot point, if you can imagine an axle going through the back here, the pivot point is going to literally, where I want the pivot point is, I want the pivot point to be literally right on, smack dab in the middle of the, or smack dab in the middle of the tire, but on the edge of the tire. Now, could I have it in the middle of the tire? Probably. And in fact, I'm going to experiment with that a little bit later on. As I go through these cars, I'm going to experiment with them and find out where the best pivot point is going to be. But for now, what I want to do is I want to have the pivot point at the edge of the car. So what I want to do here is I'm going to try to figure out a pivot point relative based upon the chassis, which means I'm going to have an X value to go all the way down to here, a Y value to go up and down, which the Y value should all be 0 because everything's going to be in the middle, and a Z value to go all the way out to the wheel, just to the edge. So let's take a look at what I did here. Here's the pivot point. Here's the X value, because I want to be the X value. Oh, and by the way, I forgot to tell you, I'm getting the X, Y, and Z from that wheel data at the very top that you have up here. There's the X and Z. In fact, we're on the back right. That happens to be the X value and the Z value. So negative X and a negative Z value and a negative Z -1 multiplier. Let's go back down. Okay, so there's my X value. That now puts my X-axis. That puts my X-axis down to here. The Y is 0, so that's no change. And then Z is going to be the Z value. The Z value is going to put me in smack dab in the middle of the wheel. And then I'm going to add the, I'm going to then, actually, I'm not going to add. I'm going to, first of all, because remember, we got to figure out, we got to do it mathematically correct here. We're going to take half of the diameter of Z, because remember, I want to be right on the outside of the wheel. So half of the diameter of Z, the radius, is going to get me to the outside of the wheel. I'm going to multiply that by the multiplier, which will put that wheel out to a particular point in the, on the outside. It's going to put the wheel on the outside of the. Let's try that again. So it's going to put I'm going to take the diameter divided by 2, because I want to get the radius, which will get me to the exact outside of the sphere. I'm going to multiply it by that Z multiplier inside that data. That will get it to the correct wheel. And then I'm going to multiply by -1, which will move it back in toward the chassis, because I want it to the inside of the chassis. And yes, I probably could have just flipped everything in the Z multiplier to be, instead of paying -1, to be 1, and it would have fit. But it's not how I think. I think, I want my multipliers to be relative to the chassis. And so since I need my point to go toward the chassis, I'm going to multiply that by -1. That will get me back toward the chassis. So that will give me, if we go back to the screen, that will give me the X down to here, the Z in the middle. We're going to divide by 2. And that's we're going to divide by 2 and multiply by the Z multiplier. That's going to get me to this particular wheel. And then when we multiply all that by -1, it's going to move it inward. So that's going to put that point right there on the edge of the wheel. And for all the rest of them, it's going to put it right there, and right there. And that will take care of the chassis pivot point. And I save all that. Everything is, all these pivot points are being saved as data for later on consumption. Then I got to figure out the wheel pivot point. And the wheel pivot point is going to be based upon the wheel pivot point is going to be based upon the pivot point as from the viewpoint of the wheel. So this is going to be a little bit easier. The X is going to be 0. The Y is going to be 0. Because if you take a look at our screen here, again, we're looking just at the wheel, not at the chassis, but just at the wheel. We're going to be in the middle. So what's the middle position for X? 0. What's the middle position for Y? 0. If we went directly in the middle, then Z would also be 0, but we don't. We want it on the side. So we're going to apply the same information that we applied up here for the chassis down, or the same equation down here for the pivot point. Now the key here is that we're already at the wheel, so we don't need to add the Z here. So we're just going to go straight to the radius, get the correct diameter, get the correct multiplier depending upon whether we want front or back, or in this case left or right, and and then multiply it with -1 to get it coming in toward the chassis. So what this ends up giving us from a local point of view is both the pivot points at the exact same point, and that's what we want. And that's saved in the pivot points. Once we have all of that set up, what will happen is when we do the constraint, we're going to give pivot A and pivot B, we're going to give pivot A as the chassis constraint and pivot B as the wheel constraint. Then we're going to give it some axes. We're going to basically say what axis do we want to put the action, for lack of a better term, on. And the z-axis is where I'm going to want to have all the action occur. I don't care about the x-axis. I don't care about the y-axis. I want everything on the z-axis. And so I have determined that both A and B are going to go on the Z. Now, A doesn't move, but B does move. So could I have maybe not had axis A there? Probably. I don't know. That's one of the things I need to kind of, you need to experiment with. This is one of those things you get to working, you sit there, okay, it's working. I'm not going to touch it. But I will touch it because there's some errors with it. The perp A and perp B are perpendicular axis. In my particular case, it doesn't matter what the perpendicular axis is as long as it's not Z. It doesn't really matter. So I've set mine for X. It could have been set for Y. It didn't really matter. Collision false just says, hey, if these two pieces of information do happen to collide, just ignore it. Which they do collide. If they will collide, then we'll ignore it. The other important thing here on the constraint, so basically that gives us, where the pivots are going to occur and what axis is the pivoting going to occur on. But the important thing is what movements are allowed upon the axis, and there are two different types of movements along the axis. The first one is a linear movement, and this linear movement says, along the axis, how much am I allowed to move on the axis? And the other one is an angular movement, and it basically says along this axis here, how much am I able to rotate? And so let's take a look at this. Basically, each one of them is going to have a min and max limit. And I want to specify, first of all, what type of constraint or what type of limit it's going to be. In this case, it's going to be the linear x. Basically, it says along the x-axis how much movement it's going to be. I'm saying there's going to be no movement, which means I don't want any movement at all along that x-axis. Same thing with the y-axis. I don't want any movement whatsoever along the y-axis. Same thing with the z-axis. I don't want movement whatsoever along the y-axis. Now, rotation, angular y rotation. Do I want it rotating around the y-axis? That would be kind of flipping very weirdly if it was on the y-axis. I'm telling it no. I don't want any angular. I don't want any rotation around the y-axis. How about the z-axis? Don't want any rotation around that. I don't want any rotation there either. And I know what you're sitting there thinking. Well, wait a minute. You do want rotation around the z-axis. Well, this is rotating. Not really on the z-axis, but on the z-axis, but not on the z-axis. It's kind of hard to... The best way to explain is, let's go to the video. Okay, so if I was to rotate this tire along the y-axis, what it's going to do is, let me just make sure I got this correctly here. Yeah, y-axis. It's going to, you can imagine it kind of flips this way. And of course, you can tell exactly what I'm doing here. But basically, if you can take the top, if you can think the circle, the top will kind of go downward, the bottom will come upward, the top will go downward, the bottom will go upward. So it's going around the y-axis, which is up and down. If it was going along the z-axis, which is this way, it's going to flip with this side here going that way and this side right here going that way. So it's flipping around the z-axis. And it's not really around the axis, it's in relationship to the axis. But what we want here is we want to go this way, which is the x-axis. So we want rotation turning this way. And that will allow me to kind of just roll around the z-axis. So in my code, I don't have any limits whatsoever, angular limits around the z. And so that is what allows me to have the rolling tires. This is very complicated. I have to admit, I had to really dive down. It took me 2 days to try to figure it all out, and I still think I don't really have it all fully in hand. So I may have to do a full-blown video just upon this. But that's a lot to go on the constraints there, because that's extraordinarily important. That's why we had to figure out what the pivot points are going to be able to determine how we're going to get everything to move. So with all that said and done, once we have built the wheels and have built all the wheels, we're going to then do that constraint. Let me go back up to the thing here. We're then going to do the set the wheel constraint, and that will allow us to have wheels there. So let's turn back on everything. And what I'm going to do is I'm going to tell it to, I'm going to hide the model. I'm going to hide the collision box, and I'm not going to hide the chest. Okay, that works. Okay, I won't hide all of those, but I'm going to turn all the I'm going to turn on all the constraints, and we're going to Control S it. We're going to save it, and we're going to go full screen. So let's turn it back on. So you can see it kind of shimmy there. That's where I'm thinking I may have a problem. Well, in fact, there's not a may. I do have a problem with it. Because let me just show you something. So it's one of those things you run something and suddenly you realize, oh, wait a minute. Hang on. I want to try something here. There we go. See how nice and smooth and pretty that was? Now that's what the constraints will do for you. It's really, really wonderful. Now, what did I do to fix that? Is I didn't have the collision box put with it. So let's go through what the collision box is all about now. So what we're going to do here is let's take back off the physics. And what we're going to do is we're going to turn on the collision box. So we're going to, we're not going to hide the model anymore. We're not going to hide the chassis. We are not going to hide the collision box. Let's save it. Let's go back to our screen. There's the collision box. Now, of course, I have no physics applied to it. So what the collision box does, in fact, I tell you what, before we do that, let me hide the collision box and explain one thing here real quick. All right, so this is our car. And let's see, it actually, the reason we have a collision box is that the car itself has about 16 different meshes to it. You got meshes for the wheels, which I've eliminated here. You got meshes for the side view mirrors. You got meshes for the body. And let's see if we can zoom in here. Oh, good. We got a good view here. You got meshes for the interior, for the steering wheel, the bucket seats, all that kind of fun stuff. So you got a ton of message. And if we wanted to be really, really super technical about it, we would have constraints for all of these different meshes here. And I'm sorry to say, I'm not going to go through that kind of work at this particular point in time. Yeah, call me lazy, but I'm not going to go through that kind of work just to get all this running, because it's a headache. So what I've done here is I've created a collision box, and I'm going to turn it back on, and we're going to refresh the screen here. And this collision box is actually what gets collided with everything. So if we were to now turn back on the physics, and we'll let it roll, you'll notice that what will happen is that it's the collision box that hits and gets all the collisions, not anything else. In fact, you can see we got a little bleed over. I'm not worried about that. But the idea here is that we got that the collision box is what gives us the ability to make the collisions. And we have tied the model into the collision box, and we've tied the collision box with a constraint into the chassis. So let's take a quick look at that right now. So collision box, we're going to turn off, since I'm going to be going back to the screen, we're going to turn off the physics again. So let's take a look at the collision box. And it's real simple. It's just a simple box. Of course, as soon as we can find it. There we go, collision box. Okay. When I load in the model, I save the model dimensions, so I'm allowed to be able to build my box based upon the model dimensions. This gets me very close to how what the model looks like. It's not perfect, as you found out, but it's extraordinarily close. Colors, that's no big deal here. Here's the interesting thing. First of all, the position. Now, everything is based upon 0 position. And what we want to do here is we want to be absolutely certain that the position of this collision box is not on the ground. By default, it's pretty much going to be on the ground. And that's going to, obviously, once we apply the physics, it's going to, scrape along the ground and nothing's ever going to move. So I've got to be able to change y-axis of it to make sure it's up off the ground. In fact, I want it to be even with the chassis itself. And so to do that, what I've done is basically I've taken the height, which is the height of the box, and I've moved it up halfway, because remember, our origin is always smack dab in the middle of the mesh. So if I want to move it up to where if I want to move it up, I want to move it up half of the width, or half the height in this case, of the mesh. So once I've done that, that works great. But then remember, we still have the chassis right there. So now I want to move it down by half the chassis. And that's what this does right here. This moves it down by half the chassis width. And that allows me to be able to, going back to our screen, let's go underneath the bottom here. As you can see now, basically the chassis has completely disappeared because the box has now covered it up. In fact, actually the model has covered it up, but that's a whole nother story right there. So let's go back to our code. Now the key here is also, because I have changed the position of the box, I want the model to be able to follow the box no matter where it goes. So I have made the parent of the model, or the model, to be a child of the collision box, so that wherever the collision box moves, the model will move with it. So, and that's just very simply by saying that, hey, the parent of the model root, which is the root mesh of the model, is going to be the collision box. But because I've done that, I've also, because we have adjusted the y value for the collision box, we're going to have to adjust it for the model root too, and that's what we've done here. And as you can tell, it's done by the exact same amount, and that's what gets the position of the mesh, or the position of the model, as close as we possibly can within the collision box, as you saw in the video. And that's pretty much all there is to that, and that's essentially it. Then it's a matter of applying the collision box constraint, which is the next routine. And that's very, very easy. I've got the pivot point A, which is going to be the chassis. I'm pivoting it. I'm connecting it straight to the middle of the chassis. And the pivot B, I'm setting up straight to the middle, or basically to the position of the model itself, and subtracting -1 from it. This is where when I was recording the video earlier, and I had forgotten to hit record button, this is where I made a mention, oh, I think this is the reason that the wheels are shimmying. This is something weird. But anyway, so that's a constraint. That's what the constraint here. It works exactly the same way as the wheel constraints. I got the pivot A and pivot B. Axis A and axis B, I don't care. Perf A and perf B, I couldn't care less. And why could I not care less about all those? Because look at my limits. I want no movement along the X. I want no movement along the Y. I want no movement along the Z. I want no rotation on the Y. I want no rotation on the Z. And I want no rotation on the X. Basically, I don't want those things to move whatsoever. No matter what happens, I want the collision box to affect the chassis in the same way. Whenever it collides, I want it to affect the chassis in the same way. And the chassis, if it collides with something, I want it to affect the collision box in the same way. And of course, the wheels are connected to the chassis. So if the wheels connect with something, it's going to affect the chassis, which is going to affect the collision box and all that kind of fun stuff. But the key here is with the collision box, it is locked down solid. I really don't even think I need all this. In fact, I know for a fact Babylon.js has what they call a lock constraint. I didn't use it this time because, I'm trying to learn exactly how the 6 degrees of freedom works. So I decided to go ahead and use this instead of using their lock constraint. But that's all there is to this too. And I'm thinking that the idea here is that this is our issue, is why it's shimmying right there. So what I'm going to do here is I'm going to do one more thing before we close out this video. To show you what some of the debugging is going to look like. And again, I've got all of this saved off in the in my carbox routine within the public repository. It happens to be car 5, as you can see up there. I've got Ferrari, car 5, car 3, car 2. This is where I experiment with everything. Ferrari works really nicely. Car 5 is my better. Is the one that's been normalized a lot better, so I can get the other cars working. But car 5 is there and working. What I've done here is I've got a static debug set for true, and this allows me to have some debug information when I set up the constraints. And this is where I'm going to show you about the world, the world pivot A and pivot B. Because remember earlier I said that pivot A and pivot B had to be local to the mesh. But the problem is that when it actually computes it, it's going to be computing it based upon the world pivot. And so the two world pivots have got to be pretty much also exactly the same. And so this debug information I got here for all the wheels and for the collision matrix, the collision box, allows me to kind of get a peek at what the world is thinking is happening. And the real big thing is this right here. I've got a debug statement that immediately, or a warning statement, comes in and says, hey, you know, you can have potential instability if your pivot points is greater than 0.1. This is why on those other videos that I showed you where I attached the model and everything went flying off to the sunset. This is why it did it, because this was unstable at the world level, and I didn't know that at the time. That's why I spent an entire weekend just diving into the 6 degrees of freedom to figure out what the heck was going on. So there we are. This is the reason why. And so I've got this little debug routine in here to be able to say, you know, hey, this might be an error. This might be an error on there. But anyway, now that we got all that, let me show you what it all looks like. So we got our debug true. I did want to hide the chassis. I'm sorry. Let's hide the chassis. I want to hide the collision box. I do not want to hide the model. Yep, that's what I want to do. And then we're going to put the, as you can tell here, I didn't put the model looks correct, but I didn't put the physics on. So let's put the physics on. And then I'm going to show you what all that debug was all about. And then we'll go back to the screen here, and let me go ahead and just refresh. Yeah, so there's the shimmy, and I think we know why the shimmy is occurring now, but I'll look at that and get that fixed. But what I wanted to show you here is that this is the debug information that comes out. I know it's kind of small. I wonder if I can increase it. I can. Okay, cool. All right. Good. Okay, I've increased it a little bit here. So hopefully you can be able to see it a little bit better. But each wheel has information, and the model has information. But the key here is, the most important thing is that I get a world pivot A and a world pivot B. This also allows me to be able to see differences between the pivot A and the pivot B and the chassis local if I needed that information. What I really wanted the information more than anything was the world pivot A and the world pivot B, because this tells me from a world point of view what the pivot should be, and these should be exactly the same. This number right here, this distance, should be 0. As you can tell, it's not quite 0. It's not quite 0 here either, or here either, or here either. I mean, it's very close to 0, but it's not quite 0. But it is 0 with the collision box. But what I noticed here, if we took off the collision box where it was going really, really nice, these numbers still were not quite there. So I've got to try to figure out if that collision box... Well, actually, let's just go ahead and do that now. Let's flick back over to the code. And what we're going to do here is we're going to not build a collision box, and we're not going to apply the collision box physics, and we're not going to set the collision box constraint. And we'll just let it go on its very way. Of course, that means that the let's also go ahead and hide the model. That should get us. Alrighty. Well, that didn't quite work because I forgot to turn on the chassis. So let's turn on the chassis. And there we are. So now notice that it works perfectly, but we still have a little bit of a distance between each of the different pivots. So I think that what I can do here is that the combination of this being slightly off and the combination of having the collision box on there is making it kind of shaky. So I'll have to take a look into there. But that's the key with that. I think that's back to 100%. But anyway, so that's the key. That's how, that in a nutshell is how it all works out. So there's my car. Let's just turn it back on. Let's turn everything back on, make it look really, really nice. Let's turn off the chassis. Turn on the model. Turn on all the collision stuff. And there we go. And there's a little shimmy and everything. So, Hey, I know this was a long video. That was a great deep dive into the 6 degrees of freedom. But as you can tell, I got it working. So one of the things I want to do this weekend is I'm going to get 3 other models working. I'm also spending a little bit of time to try to fine tune the physics a little bit so I won't get that little shimmy in the wheels. But that's basically all that's going to be here. When I make it, I'm going to make it the final video. Hopefully, be able to show you a race with some real cars in it. So, hey, thanks for sticking around. I hope you enjoyed it. If you have any questions or anything, please leave a comment. And thanks again. Thanks for watching. Subscribe to this channel to view more videos. Click on the like button on this video and visit us at TheVirtuoid.com. Also, support us on Patreon, where you can get access to member-only videos. Links are down below. Again, thank you very much for watching, and keep on coding.